All right, hello guys, I'm back. I know that you got used to not having me make these, but we got another one. Like I said, when I can, I try to make these, and I will try to keep this one short, so let's go. So absolute dating by the use of radioactive isotopes. So we're actually gonna come up with an actual number of years, or it could be days, it could be minutes, but in our case it will be years, for how old things are. And we're gonna see how scientists have been able to do this. So like, why is the Earth? Why do we think it is around 4.6 billion years? And how do we know how old other things are? So that's the question we're gonna try to answer here. So unlike relative dating that we learned already, absolute dating is going to be where we can actually get the age of a fossil or a rock, or in some cases a meteorite, in actual years. So that's kind of the key point here. So absolute dating is going to be given in an absolute time frame, not relative. So before we would say this rock or this layer of Earth and all the rocks in it are going to be older than the layer on top of them. But that was all relative. We couldn't give an actual date. So we'd have to use terms like before, after, early, late. And we can get a relative idea of how old things were. And we knew that we could kind of get in the range, but it wasn't until scientists started being able to absolutely date fossils in the geological time record in the soil that we could actually date how old things were. This does not, and we're going to talk about this in the end, it does not mean it is not without error. Okay, this is still a pretty approximate, and you'll see why. We'll talk about it at the end, but this is not perfect. So you do want to write all this down. One thing you should know for this lecture is you probably will be writing most of the information on these slides, because it's only 10 slides, so it's jam-packed with all stuff you guys need to know. So radiometric dating is the most common type of absolute dating, so that's what we're going to spend most of our time with. So when I refer to absolute dating, I'm basically referring to radiometric dating. There are a couple other methods, but this is what we stick with. So let's talk about radiometric dating. Before we talk about anything else, you guys need to know a little bit more. We kind of talked about this at the beginning of the semester, but let's make sure we understand. So, first of all, you do want to write this entire slide down, okay? And I know that might take you a second, so pause if you need to. But basically, let's go through it. So you're going to have a chemical symbol. This will be directly from the periodic table. This could be C for carbon, or it could be N for nitrogen. Whatever's up there, that's what it's going to be. And then the mass number is going to be on the top. This is going to be a number that is the addition of the protons and neutrons. And then the atomic number will be below. The atomic number is the number on the periodic table that's big. So hydrogen is number 1, helium is number 2, lithium number 3. So you might want to take a look up at the periodic table right now and just make sure you can make that connection. So that'll go here. So if this element, so this is how we would draw this. So if it was carbon, okay, and carbon will always have an atomic number. This doesn't change, of 12. But what might change is its mass number, because that's the protons, which is also, the proton number is the atomic number, by the way. The proton number is the atomic number. So we talked about that before. It's the big number on the periodic table. So if carbon is 12, you guys should all look up on the board. Whoops, I actually messed that up. My bad. Carbon is actually 6. So some of you should have been like, what? But yeah, carbon is 6. So if we're looking at an isotope of carbon, this cannot be 12, and let's see why. So in a neutral atom, carbon's mass number would be 12, but it's not in this case. In this case, it could be a really common isotope of carbon that we actually do use for radiometric dating, carbon dating, is carbon-14. And so this is because it's going to have 2 additional neutrons in its nucleus. Right? Because where is this 14? Well, 6 plus 8 equals 14, right? So that means it's going to have 8 isotopes, because remember, it's protons plus neutrons is going to give you that number up here. So if we know we're always going to have 6 protons, that's given by the lower left number. That means that the neutrons have to be 8 to equal 14. And because these numbers are not equal, we have an isotope. So whenever these numbers are not equal, it's not a stable element, and it's we call it an isotope. The number of, and you know this, the number of neutrons is different than the number of protons. So hopefully you guys wrote all this down. I don't need to spend too much time going over it. The number of protons in an atom determines which element it is. We already talked about that. If you change the number of protons, the element changes and the mass changes. So if we ever change this number down here on the carbon, so if I draw it a little bit bigger over here, if we have carbon 14, if we ever change this number down here to 7, well, then it changes the whole element to nitrogen, okay? And if we're dealing with a stable isotope, take a second to ask yourself, what do you think, if we're dealing with a stable isotope of nitrogen, what should the mass number be? Take a second. It should be 14, right? So that's if it's stable. But oftentimes in nature, elements are not stable. There's a lot of elements even around us right now as we speak that are unstable isotopes. So if you change, so we're down here, if you change the number of neutrons, the element stays the same, but the mass changes. So that's the mass number. So when we change the number of neutrons, the mass number will change. But remember, this bottom number here will stay the same as long as we're dealing with the same element. So isotopes are atoms of the same element that have a different number of neutrons. This should be, so some of this stuff is new, but this should not be new. You should know this. This was on our first quiz of the year, okay? So make sure you understand all that. Let's keep moving on. So why are some isotopes radioactive? Well, it all has to do, like I said, with stability. So you need to understand that isotopes are unstable, and this makes them radioactive. So if they have too many neutrons or not enough, this makes them unstable, and they will do something to become more stable. So the nuclei of these radioactive atoms, so when something is unstable in its nucleus, so remember you have your neutrons and protons in the nucleus, if there's an imbalance here, let's say if you have more neutrons than protons, or the other way, you could have more protons than neutrons, both of these are isotopes, okay? Remember, because it's just when the number of protons is different than neutrons, and this is in the nucleus. So whenever that number in the nucleus is not equal, you will have a radioactive atom, okay, because it will be unstable. So there's radioactive atoms all around us, but it matters what elements we're dealing with, because there's some atoms that are radioactive, like when you eat a banana, you actually are getting some radioactivity, but it's not enough to hurt us. Only some elements emit enough, and depending on what we're doing with those, like if we're launching a nuclear missile, then the radioactivity will go way up, because there's a lot more. That's actually what they're doing, is they're messing with the nucleus, and that can cause a lot of radioactivity. But like I said, most radioactive particles don't harm us, even though we tend to think of them, you know, as harmful, but most don't. It's only when we kind of mess around with them that they get more radioactive. So they will decay, and this is another key term you need to know. They will decay until they have reached a stable state. So we're going to look more at what does that mean, decay. So during radioactive decay, again, most of these slides, you probably want to write most of this material down. So I know this is going to take a little bit longer. So during radioactive decay, the number of protons in the atom changes, and one element transforms into another. So they will do this in many different ways, but the gist of it is you're going to start with your radioactive parent isotope. So this will be the unstable one. And what will happen is they will decay into an more stable, not always completely stable, but a more stable daughter isotope. So it's like popping corn, okay? When you start heating these kernels up here, you add energy, they're unstable, and what do they do to become more stable? They pop, right? And they become something different. That's basically a really good analogy, and we're actually going to be doing our performance task is going to have a lot to do with this here. So stay tuned for that. But each radioactive parent always decays to a specific daughter. So we've actually mapped these pathways out. Chemists and physicists have mapped these pathways out. There's no way to predict which atoms will decay first. So we don't know which of these kernels, or in this case parent isotopes, are going to pop first. And you guys know this. If you were popping a bag of popcorn in the microwave, you wouldn't know. You wouldn't be able to predict which kernel was going to pop first. It would be kind of random. But we know some pop more than others, and that's why sometimes when you don't heat it all the way, you have a lot of kernels unpopped. So radioactive atoms decay at a specific rate. This is the key here. So make sure you write this, highlight it, underline it, whatever you need to do. This is how radiometric dating works. Okay, radioactive atoms decay at a specific rate. So this is how we're able to, if we can measure that rate, and we use a little bit of what we call uniformitarianism, that we think that if they keep decaying at this rate over time, and they have always decayed at this rate, then we can count backwards. Okay, so we'll look at how they do that. Because once they decay, they cannot change back. So how long does radioactive decay take? Well, every element is going to be different for every different parent isotope. So for every unstable atom, the half-life is going to be different. But the time it takes for half of the material to decay is called a half-life. Okay, so it's the time it takes for the half of the radioactive or parent isotope in a sample to decay to daughter isotopes. So because it's half-life, okay, each parent, this is something you need to know, each parent has a 50% chance of decaying during one half-life. So if we think back to our popcorn kernels, each of the kernels in a bag of popcorn will have a 50% chance during a half-life of decaying into the daughter isotope. Okay, and we'll take a look at what that means in the, like a better picture of that. But this can be measured. Some half-lives are measured in seconds, some are in minutes, and the ones we're going to be using in geology are in the years, and more specifically the millions of years, because remember, geological processes take a really long time. So we have to use isotopes with half-lives that are very long. So you can see some elements, we can go from thousandths of a second to billions of years, depending on what element we're looking at, what unstable parent isotope we're looking at. So what starts the stopwatch? So when a mineral, this is going to be really important. So when a mineral is deposited, most of the atoms are not radioactive, okay, in a mineral. So when we look at a rock, we take a look at the specific minerals and we look at the atoms in the mineral, okay, and scientists have, and I'm not going to go through how they do all of that, but you need to know that most of our minerals are not super radioactive. But what we do, so all the non-radioactive atoms in this mineral are like all the gray area. But then in this mineral, you may be able to find a couple atoms that have a radioactive isotope. And so what we can do is once we see all these radioactive isotopes, we can look at the stable atoms of a stable daughter isotope over time. So we know that if there's this many parents, so over time, the parents are going to decay to daughters. So you can see here 50% here. So starting here, 50% decayed into green. So it should be 50-50, half and half. That's because after one half-life, 50% decay. After two half-lives, the remaining red ones here decay into green ones here. And then after three half-lives, all the remaining red ones you can see decay into the last two, and only two parent isotopes. All the green are daughter isotopes. Okay? And one thing I need to add here is that in geology specifically, what sets the clock is the cooling process. So when cooling of magma, this starts the stopwatch, okay? So this is really important to know because remember when I said that Earth is about 4.6 billion years old? And I said, well, what is that actually? It's not like Earth just popped out of nowhere. This is when we think Earth, some of the oldest rocks we find on Earth actually cooled. And that's what started the stopwatch. So when we say Earth is 4.6 billion years old, we're actually measuring when those really old specimens of rock actually cooled down and started this stopwatch we see here. So if we measure a really old rock on Earth, then we can see some of the oldest ones are starting that stopwatch. We can count back the half-lives and see when these minerals cooled down. So again, it's not that Earth just popped out of nowhere 4.6 billion years ago. It's that it kind of cooled down, and that's when some of the oldest rocks were formed. So from magma. So it's really important to know that different isotopes we look for can give us different ages. Okay, and so and just so you know, all of these have different numbers here. Do you guys have any idea what those numbers refer to? Well, if you remember back, it was so if we look at carbon 14, that's the mass number. Okay, so the number next to them is the mass. So you know you're dealing with an isotope. Let's take potassium, for example. Potassium's atomic number is 19. Okay, well, what's 19 plus 19? Anybody quick at math? It's about 38, right? But this is potassium 40. So you guys should know right off the bat that because there's not an equal number of protons to neutrons, the mass number isn't 38, it's 40. That means this is an isotope. So just remember that because that's going to be important. So anyway, these different ones take different amounts of time. Potassium 40, for 50% of any sample of potassium 40 you have to go to argon 40. This is the daughter isotope. So what we do is we measure how much argon 40 there is relative to potassium 40. And we know if there's half and half, that took 1.25 billion years. If there's more daughter than potassium, let's say there's 2 times more argon than there is potassium, then we know that's going to take about 2.5 billion years. So you can see that different elements will give us different amounts of time that we can count back from. So rubidium is 48.8 billion years. So that's a really long time. In fact, this should give some questions. This is longer than what we think how the universe has been around. So if we think the universe has only been around for like 13 billion years, rubidium takes 48.8 billion years for half of it to decay. That raises some good questions. But anyway, so you can see we use different ones. If we wanted to map out how old we thought the solar system was, or the universe, maybe we use thorium-232 because it's right around how long we think it is. So anyway, all this stuff you should probably write down. If you measure the ratio of parent to daughter isotopes, you can determine how many half-lives have passed so you find the half-life of the parent isotope and you can count backwards. So what you need to know is the number of half-lives and the length of the half-life, and then you can get the age of the sample. And we'll do some practice problems on this. So this is just a good analogy for how these isotopes will age, and because atoms don't age the way we do, especially if they're unstable isotopes. So you could take these these baby atoms, you could think of them, they're baby aliens. Let's say we start with 16, and they're really unstable. So after one half-life, 8 of these babies have turned into, have gone through their first half-life. And if their first half-life takes 70 years, then that means after one half-life, they will be 70 years old. So they're already pretty old, I mean, compared to humans. But after 2 half-lives, only half of this group will decay even further into 140 years. And then half of that group will decay into 210 years old. And then of the remaining 2, only 1 will have decayed into after 4 half-lives, 280 years old. So he'd be 280 years old. So hopefully that kind of makes sense. That's basically how atoms age. And so this old guy, this is actually, I've noticed this when I had put up this slide, this is actually incorrect because this old guy should be, after 4 half-lives, would be with only the remaining 8 that didn't decay up here. So remember, 8 of these guys turned into that, so they're no longer here. So this picture's almost perfect, but he should be sitting here. This old guy is only sitting with 8 of these people, 1 of these guys that's a little bit younger than him, 2 of these guys that are even younger, and then remember 4 of these will still be at around 70 years because only 50% in each half-life will decay. So that's how it works. Okay, so how to choose which isotope. I kind of already talked about this, so I'm not going to spend too much time on this slide, but you want to estimate the age of your sample. So if you think it's something that's really, really old, maybe, as old as the Earth, then you would want to use potassium-40. Rubidium-87 can be used for anything super old because its half-life is so long, but maybe you might not want to use that for most things because most things in our universe apparently aren't that old. But thorium could be 232, could be good for estimating the age of the universe. Uranium-235, this could be good for, say, like dinosaur remnants. Uranium-238, this could be used for the age of the Earth and the universe because it's 4.47. Carbon-14 is going to be really good for more recent dates because it's only 5,000 years. So carbon-14 is actually something we use to date samples that were once living. Okay, so we use carbon-14 a lot in dating fossils as well, especially more recent fossils. So there you go. All right, so let's do a couple quick practice problems. I'm gonna go through these pretty quick because I know I'm taking a lot of time now, but I'm gonna show you how to do these problems. So you wanna write all this down in your notes, and then we'll have a worksheet on this and you'll actually have to do the math yourself. So let's do 2 different kinds of problems. So the first one, the half-life of zinc 71, so Zn71, remember this is its mass number, is 2.4 minutes. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes has elapsed? So the first thing we need to do is figure out how many half-lives this has gone through. So we know one half-life takes 2.4 minutes and it's gone through 7.2 minutes. So the first thing we need to do is take 7.2 over 2.4, and that will tell us how many half-lives. And it turns out most of the time I'll give you really easy numbers to work with. This ends up being exactly 3, and we did that on purpose, okay? And so we know this went through 3 half-lives, so that's the first step. So we'll say that's step number 1, so you might want to write that down. So it went through 3 half-lives. Okay, so we know this is the second step. Anytime you're dealing with how many half-lives something's gone through, you're going to use the same equation. It's going to be 1/2 because it's a half-life, so that will always be the same. And we take that to the power of how many half-lives. So in this case, it'll be 1/2 to the third. Okay, and if you type 1/2 to the third in your calculator, you put in 0.5, and then you put the little caret, and then a 3, and I can show you how to do that in person if you need help. But 1/2 to the third power, that's going to end up equaling 0.125 when you type it in your calculator. Okay, and then the last step is we're going to take, this is a fraction of how much is going to be left. So we want to know if one had 100 grams at the beginning, after 3 half-lives we figured out, we're going to have 0.125 of that left, right? Because it went through 3 half-lives. So this 100 grams has halved itself 3 times. And so the easiest way to do this is we just take 100 grams and we multiply that times 0.125. Okay, and I'll do that on my calculator really quick. Pretty easy calculation here. So it's 100 times 0.125, and we get 12.5 grams is left after 3 half-lives. Okay, so that's one type of equation we'll do. There is one other type of equation we could do in this. I could ask you the question, I could ask you 2 questions. I could say, how many neutrons are in this sample of zinc 71 before it decays or anything like that? So remember, so the zinc is decaying into its daughter isotope, so only 12.5 grams of zinc 71 is left, and the rest of that 100 grams has turned into its daughter isotope. But for this question, so another question I could ask is, what is the number of protons? Would be a good question. You need to know how to do this. What we do is we know the mass number is 71, right? I'll do it up here. So we know the mass number is 71, and we know that the mass number equals the protons plus neutrons, right? So this 71 is the mass number, and that equals protons plus neutrons. So in order to do this, if we want to get how many neutrons, which was I meant to put how many neutrons. The protons is just the mass, is the atomic number. So that should be, the number of protons should be easy because you just look at the periodic table. The neutrons, what we'll do is we'll take 71, and let's take a look at that. What is zinc's number of protons? It's 30. So we know 71 minus 30 is going to give us our number of neutrons, and it is 41 neutrons. Okay, so that is another type of problem. So let's do this last problem on this page. So this one's a little bit, it might be tricky because there's less you have to do here, because we're saying how many grams of a 10-gram sample would have decayed after exactly 3 half-lives. So they give you the half-life of 21.5 hours, and I may give you a question that's kind of tricky like this. You don't even need to use that because they already told you it's 3 half-lives. So we get to eliminate step number 1 above. So we can eliminate that. So what's 1/2 to the third power? Well, again, it's 0.125. And if we multiply that by 10, which is step number 3 up there, right? Because we started with 10 grams, and we know what 0.125 of that is going to be left. So 0.125 times 10. Oops, hang on, I messed it up. So 0.12 times 10 on my calculator is 1.25 grams would be left of this sample. And I could do the same question. OS 182 has a half-life of 21.5 hours. So I could ask you how many neutrons are in OS. So you'd have to find OS on the periodic table. It's number 76, and you would have to say, okay, well, 182 minus 76 will give me, and I might actually test you on this, so make sure you know. So that would be how many neutrons are in OS 182. All right, so those are the 2 types of math problems you might have, and let's go ahead and finish up this with our last slide. So you should have some questions, okay? You really should have some questions about this, about the accuracy, and I told you I'd talk about this at the end. So this is still based on this concept of uniformitarianism, okay, which says that things should be the same throughout time, or maybe we'll be more specific, processes that occurred in the past will keep occurring the same way. The problem is with this, and you know, is this something we should rely on? Should you be skeptical? And the answer is yes, you should, because maybe one question that should have come to your mind is, have we been around for 1 billion years? No, we haven't, right? So how do we know that the decay rates of these isotopes are occurring exactly the same over time, right? So that's a really good question, because we haven't been around for billions of years, and a lot of these isotopes we use take a lot longer than, you know, we've only figured this out in the last 100 years. So nobody's been counting these half-lives over time. So how do we know? Well, basically what they do is they do a lot of, the best answer I have for this is they do a lot of samples. They do a lot of testing on different isotopes. And so when they date something, they don't just date it based on one isotope. They look at many. And what they find is that everything kind of comes out and checks off. So if we use carbon-14 to date a sample that is really old, then that carbon-14 dating should give us the same age as, say, using a uranium isotope of the same sample. And what happens is when they do this with many different samples, and you know, after knowing their half-lives, after calculating their half-lives, when they get the same age using all these different isotopes, it's kind of hard to deny that the radiometric dating is working. But there is some questions, and there is some, you know, there's some approximations made, and we have to assume, again, so this is an assumption. I mean, it's very hard to actually prove, because no one's been around long enough to witness a lot of these half-lives, almost any of them, the longer half-lives. So it is an assumption, and that should raise some questions, but it has been tested enough for scientists to think that it is reliable. So, but you know, you should always be skeptical, and one of the next lessons we're going to do is going to be on, you know, how we think maybe scientists got it wrong, and it's a pretty interesting topic to explore. So stay tuned, and make sure you guys write all these notes down, and yeah, I'll see you next time.